So what I'm going to talk to you today is looking for dark matter interactions, and what I mean is the fundamental interactions that we look for in particle physics. I want to look for dark matter scattering with the standard model, and but instead of going to a direct detection experiment, I'm going to use cosmological observables, and it's this interesting fact that cosmology has gotten so precise, or the data has gotten so good, that we can actually use these observations in cosmology to say something about the particle nature of dark matter. So here's the outline of my talk. The first thing that I'm going to do is talk about the standard role that dark matter plays in the early universe, and how dark matter goes on to form structures in the universe. And then I'll introduce this effect of dark matter scattering and how that affects cosmology, and look for these effects in the cosmic microwave background and with satellite galaxies of the Milky Way. At the very end, I'll come to this experiment called EDGES that is looking at 21 centimeter signals in cosmology, and they have a purported detection, and I'll explain what all this has to do with that experiment. Okay, so let's get into it. The role of standard dark matter. This is the depiction of the timeline of our universe, so starting here at the Big Bang and going to today. And we usually work in redshift, so redshifts, low redshifts are closer to present time, larger redshifts are later. And at the very beginning, the universe was very hot, dense, it was ionized, and Big Bang nucleosynthesis gave us our first light elements, so mostly hydrogen, some helium, and even less of higher elements. So I'll focus mostly on hydrogen and helium, just assume the universe is made of that. And it's not until this process that's called recombination, when you have electrons and protons able to get together and form neutral hydrogen, can we see any signal. So all the photons in this ionized period of the universe are scattering on electrons and changing direction. And once neutral hydrogen forms, that radiation is allowed to free stream to us today. And this is the cosmic microwave background radiation that we see. So all the physics that was happening at this point in time, at the time of recombination, is imprinted on the CMB sky. So we get a direct picture of what was happening at this era. And so once neutral hydrogen forms, we enter this period called the Dark Ages. And the Dark Ages, there's not a lot happening that we can hope to observe. The universe is mostly neutral hydrogen, and so it's dubbed the Dark Ages. And it's not until this period called Cosmic Dawn, when the first stars have formed and start emitting very high energy radiation, that we can hope to see a signal. So at Cosmic Dawn, we have the stars turn on, and this radiation goes and reionizes the universe. Okay, and so then we have today's galaxies, and we can look to see the properties of various galaxies, how many of them there are in our local area and beyond. And so today I'll focus mostly on very, very early times and later times in cosmological history. Then I'll also, at the very end, come back and touch on this era of Cosmic Dawn. Okay? So, all this structure for today's galaxies are formed because of dark matter. Dark matter is what seeds structure formation. So what do we know about dark matter? And much of it comes from the cosmic microwave background. And I'll get into what all this is in just a second. But in terms of our observations, we see that in a standard lambda CDM cosmology, so meaning that cold dark matter is assumed to be distinct from baryons, one, so it can't act as normal ordinary matter. Namely, it can't scatter a lot on photons. So when cosmologists say baryons, what they mean is electrons and protons and helium, so not just the standard baryon. So when I say baryons, I mean all of these objects, or potentially all of these objects. Yes, so CDM stands for cold dark matter. It's assumed to be non-relativistic, and it's assumed to have no interaction properties at all. So it's completely collisionless, and it's about 6 times more abundant than ordinary matter. So dark matter truly is the seed for structures of matter in the universe. It forms gravitational potential wells for the normal matter to fall into and form galaxies. Okay. So in terms of what's happening in the early universe and how we can decipher what's going on in this CMB map, we have to go to this very simple picture. So imagine if you have a clump of dark matter here. So it's going to create a gravitational potential well. And we have a dark matter clump here and one here. And we have baryons that are colored in purple. And they feel the gravitational pull of the potential well. So the baryons are going to want to infall. But this is the early universe before recombination. So there are also photons that are around. And so photons will also interact with these protons and electrons. And these photons are going to want to push these particles back out of their potential wells. Okay, so that's the heuristic description of what's going on in the early universe. We can imagine that these wells are placed at different scales. So you can imagine here's a dark matter well and here's a dark matter well, or maybe they're spaced more closely. And in any of these scenarios, you have this oscillating behavior. They're just simple harmonic oscillators that are describing the motion of the baryons and the photons in these potential wells. So this is just a Fourier space description of what's happening in the early universe. And at the time of recombination, when your photons and your baryons stop interacting, wherever these baryons are at that time, they get frozen in. So wherever they are in this oscillation, they get imprinted on the CMB. So that's how we can kind of tell what physics is going on at early times from the cosmic microwave background. Okay. So this is dark matter, and if I want to take seriously the idea that it should be some sort of matter component of the universe, then it should have properties of that normal matter has. It should be a particle with some mass. Maybe the dark matter is comprised of many particles. Maybe there are new forces that are dictating these interactions between dark matter particles. So one of the long-standing paradigms for what dark matter is has been the weakly interacting massive particle, and that has driven a lot of our search strategies for looking for dark matter interacting with ordinary matter, with us. So the search strategies are often summed up in this Feynman-esque type diagram where we have 2 standard model particles and 2 dark matter particles. And depending on how you read the Feynman diagram, it will tell you a different search strategy. So if you read going from top to bottom, this is the production of dark matter. 2 standard model particles come in, maybe 2 dark matter particles come out, and we can maybe see this at the LHC. The inverse process is annihilation. So this is indirectly detecting dark matter, annihilating into visible standard model particles. What I'll be mostly focusing on today is the idea that dark matter can scatter on a standard model particle. Yes, this is the concept used in direct detection. So I'm going to give a very quick primer on what direct detection does, or what the research idea is. So we are somewhere in our Milky Way galaxy, traveling at 220 kilometers per second. So in our frame, that looks like a whip wind that's coming at us. And so experimentalists built these very large detectors of, say, liquid xenon, and put deep underground. And what they're looking for is a dark matter interacting with one of the nuclei of the target nuclei of the experiment. And the hope is to measure this recoil of it. So this is directly detecting a dark matter interaction with us. So the rate at which this process is expected to happen depends on a few different properties. It depends on astrophysical properties, like what the local dark matter density is, what the velocity distribution is in the Milky Way. The particle physics aspects come into it. What is dark matter mass? What is the cross-section of this process? But it also depends on the experimental setup. Which target nucleus did you use? And what your detector threshold is. How well can you see this nuclear recoil? Okay? So there are a lot of different possibilities with which you can say dark matter interacts with a standard model nucleon. And so how are we going to organize this and say, and look systematically at the different types of interactions that can occur? Okay. So for this, I'm going to look at non-relativistic effective field theory. So this is a formalism that was specifically developed for direct detection theorists. And the idea is that you have some effective Lagrangian that's going to break down the interaction in terms of a dark matter bilinear. So there's some dark matter states here and an operator that's acting on the dark matter states. And then you have the same thing for your nucleons. Okay? So this is your effective relativistic Lagrangian. So when you take the non-relativistic limit, there are a few observables that you can condense this interaction down into. So two of them are the dark matter and nucleon spins. So you just fix that in your theory. There's the momentum that's transferred in the scattering event. And there's the relative velocity of the incoming particles, or a component of. Okay, and so these are the four observables that can be used to describe this interaction in general. So you can consider just an operator that is connecting in state to out state. And this operator, you can power count and say that it's going to depend on this relative velocity to some power, and it's going to depend on the momentum transferred to some power. Okay? And so these authors here have all come up with a list of 15 operators that you can describe in this way from various bilinears you can create from this effective Lagrangian. And this alpha and beta change depending on what model you're considering. Okay. So a very simple example is what's called spin-independent scattering. This is just if you have a Lagrangian that looks like chi bar chi and bar in. This has no spin dependence, and it has no momentum or velocity dependence. So the operator connecting in state and out state just looks like this. Okay, so this is one of the simplest examples that you can give. This is the scattering operator that is used by direct detection experiments to show the limits on dark matter interactions. So here are some of the latest limits that we have from various direct detection experiments. Here's the dark matter nucleon cross-section in centimeters squared. This is the dark matter mass in GeV. And this shaded region is the exclusion region. There are plenty of other experiments that are in this shaded region. I just took the outline of what seemed to be the latest and greatest at the time. So one of the things I want to point out is that there's this mass threshold at about a GeV. Okay, so all these experiments kind of start losing sensitivity right around a GeV. And this is because we're looking at scattering of dark matter particles that are bound to our Milky Way halo, right? So if you want enough momentum transfer to be able to see that nuclear recoil, this mass has to be above a certain amount, or else it just doesn't have enough kinetic energy to impart. If you have a lower mass, you would need a higher velocity, and that velocity would kick you out of would kick the dark matter particle out of the galaxy. Okay, so there's this mass threshold, and people are looking at ways of pushing this mass threshold to be lower and lower. But this is kind of the standard nuclear recoil experiment threshold. And there's also what's called a direct detection ceiling. So these experiments are probing very, very small cross-sections. So we're looking at 10 to the minus 46 centimeters squared. This is a very weak interaction, but if you imagine going upwards and increasing the cross-section to be relatively high, then you face the problem that you've built a detector and you've placed it underground, but you have the dark matter that needs to traverse the atmosphere of the Earth, needs to traverse, whatever amount of ground that you've buried the detector under, and then it has to get to the detector. So if the cross-section is too high, it will just simply be stopped before actually reaching the detector. So there's at some point, these direct detection experiments lose sensitivity because of that. Okay. So given that these limitations exist because we were really looking in sort of the prime WIMP region for what dark matter should be, there's a whole bunch of parameter space that you can imagine that's being unexplored at this moment. So this is where I want to say that cosmological observables can actually give us very complementary search regions to what direct detection is doing. And so we can search for this exact same physics that is used in direct detection or is looked for in direct detection and look at cosmology and see what happens there. Okay? So let me talk about what happens when you have this dark matter nucleon scattering in cosmology. So if we now imagine our dark matter potential wells, this is actually a clump of dark matter particles. Okay, so if we have this baryon, for instance here, this falling in and out of this potential well, it can interact with one of these dark matter particles and kick it out of its own well. And so if this process is allowed to happen over and over again, you can imagine that this interaction is going to completely break up small bound structures of dark matter and just destroy these small structures. So this is the name of the game. You're looking for small scale structure suppression, right? But keep in mind that these over densities of dark matter are the things that are going to go and seed galaxy formation. So if you've broken up these very small structures, that means those structures cannot then go on to produce and form a galaxy. So this is shown in this simulation here. Here's a larger host galaxy, and here are smaller satellite galaxies. And this is under the standard lambda CDM cosmology that's typically assumed. And when you turn on a large small-scale suppression of a very generic sort, this is what you get instead. So you can see that all these small structures have now disappeared and you have completely washed them out. They don't form at all. Okay, so this is something that we can test by just looking at the smallest galaxies and say, well, we definitely need to have dark matter. Anything that's going on with dark matter can't destroy the structures that we definitely do see. So that places a limit on how much interactions there could be.
Do you know roughly what cross-section you would need for that picture?
For this picture?
Yeah.
So this picture was, this is an old simulation. And so I think that this was done, yeah, unfortunately, so I don't know the scale of these objects, so that matters. So I don't know how much interaction you would need to get this particular picture, because I don't know what that galaxy is. But this is just sort of a very generic description of what should happen. I'll get into more numbers in a second with our actual Milky Way. Okay. So let's start with the CMB. So this is Planck 2015 data. This is the latest data at the time that I did this work. So here are the maps that the Planck satellite took of the CMB. This is the temperature and polarization anisotropy maps. So all this is showing is just the temperature variations of the CMB photons. So the CMB is very uniform, about 2.7 Kelvin. And these are all the very tiny fluctuations around that value, okay? So we need to take this map and put it in a more quantitative and statistical form. So this is the power spectrum for the Planck data. So we take this anisotropy map and look at 2-point correlation functions on the sky. So we say at a particular angular scale, say like at a degree, how correlated are this point and this point in the sky, and average over the entire sky. And that gives us this, this correlation function, okay? So this angular scale you can think of, this is at the top, but it's more convenient to use multipoles. So we have a spherical sky that we observe, and we can decompose it into multipole moments. And so I'll often just refer to the multipole L. The only important thing here is that higher multipoles mean smaller angular scales. Okay. So if we now take the best fit lambda CDM curve, which fits the data very well, and say, well, now we want to add in some sort of dark matter nucleon or dark matter baryon scattering. What is that going to do? So if I turn on a lot of scattering, this is what happens to the CMB power spectrum, right? So this is very much ruled out. This cross section is orders of magnitude beyond what the limit for Planck data puts on this type of interaction. So you have small effects that that are subleading. There's an enhancement of this peak. All the peaks slightly shift. But the main thing that you're looking for is this suppression at larger multipoles or smaller scales in the sky. Okay, so this effect is what's going to drive the constraint on this type of interaction. So we are talking about dark matter baryon scattering. Just as a reminder, we're looking at hydrogen and helium nuclei. But I have to, once again, assume some sort of model, right, that I'm for this interaction. So what is the particle physics input that I need to provide? And this is where I harken back to the non-relativistic effective field theory and just take their formalism. We're definitely non-relativistic, and say I can directly use their formalism and look at different effects, look at different types of interactions that have been parameterized by this power alpha and this power beta. Okay. So what cosmology cares about is called the momentum transfer cross-section. So you can imagine if you have two particles and they're going to scatter and they far forward scatter. It just looks like they pass through one another and nothing happens. So that the CMB is not going to be sensitive to. That effect is not going to change anything in terms of the overall motion of the dark matter or the baryons. So the momentum transfer cross-section just preferentially weights backward scattering and devalues the far forward scattering. So this is the quantity that solving the Boltzmann equations insists on having. And the important part here, which is essentially the dark matter response function, this is the going to condense down into terms of some constant, sigma naught, times the relative velocity to some power. And these powers directly correspond to which particular model you're thinking of. Okay. Helium is not a point particle. We assume that the proton is, but helium is not, and so there's some very, very small velocity dependent correction for helium to account for its form factor. But that's nearly completely negligible for cosmology. So we can treat everything as point particles and then look to see what the effect is in cosmology. Okay. So it turns out that the cross-section is not the fundamental quantity that the CMB cares about. What is important is the rate of momentum transfer between the overall dark matter fluid and the baryons and photons. So the rate of momentum transfer depends on a variety of things. It scales, it's the scale factor of the universe. The number of targets you have, so you have the number density of baryons appearing. It will depend on this cross-section, or this constant part of the cross-section here. This is just the reduced mass of your dark matter nucleon system. And here is some thermal velocity. And this thermal velocity is where all of the model dependence enters for this rate. And this thermal velocity is just, the thermal velocity is if you had an ideal gas and you were asking for this gas at this temperature, what is the velocity of the particles? So this velocity is just like square root of temperature over mass, okay? So the dark matter temperature enters here, so the CMB depends a little bit on heat transfer because of this dependence, but it's mostly the momentum transfer rate that's important. So we can look at this. Instead of looking at an equation, what does the momentum transfer rate look like as a function of time? So here's the momentum transfer rate, and I'm dividing out the expansion rate of the universe. And then I'm taking this as a function of redshift. So higher redshifts are earlier in time, and so this is the highest redshift about which that Planck is sensitive to. And this is going down to a redshift that corresponds to about recombination. So at this line of 1, if you are above this line, it means that there's a lot of scattering that's happening. So the scattering process is very efficient. If you're below that line, it means that Hubble expansion is winning. All right. So we can look at different models and how the different velocity dependencies change the behavior of the momentum transfer rate. So here, for instance, is some v to the power 4. So you can see that a lot of interaction is happening at early times, and much, much less interaction is happening at late times. All right? And we can do this for a variety of velocity dependencies and even go into negative powers. And we have to go all the way down to v to the -4 to actually get this rate evolution to flip sign in terms of its slope. So at early times, there's less interaction compared to late times. So this will be an interesting specific case to look at. So these are all early times sort of scattering models. These are late time scattering models.
And it only depends on the dark matter temperature, not the baryon temperature?
Oh, yeah, so the V thermal is both the dark matter and baryon temperature. So it's square root of T dark matter over mass dark matter plus T of the baryons over mass of baryon.
Okay.
So it depends on both. Okay, so I'm cheating a little bit here in terms of just showing you the answer. So the sigma naught is set at the 95% confidence level upper limit that I have found from fitting to Planck data. So you can see that all of these lines are kind of clustering at the same location. And all of this is saying is that at this redshift, this is where Planck happens to be the most sensitive. So Planck is constraining these models mostly here and saying that you can't have a momentum transfer rate that's much larger than 10 to the -1 of Hubble, for instance. So all of these models are consistent with a 95% confidence level. With Planck if you have a lower cross section, despite what's happening at earlier times versus later times.
Can I translate that to the specific angular scale?
Yeah. So the way that this typically goes is that at a certain redshift, there's going to be a specific mode that enters the horizon at that time. And so the size of that mode is going to give you the scale that you're concerned with. So that kind of translates to some angular scale or multipole moment.
Is that around the tail of the Planck?
Yeah. So this region right here, so Planck data is most sensitive to L of about 1400. Mm-hmm. So that is more or less kind of where this is lying. Okay. So now, instead of me showing you this plot, let me translate this into a constraint plot of dark matter parameters that people are more familiar with, perhaps. And so we can look at this dark matter physics and fit to the CMB. So I want to break this up into two different sorts of categories. We saw that there were early time scattering models and there were late time scattering models, and so they need to actually be treated fairly differently. So let me just focus on any of these models that scale as a velocity to the power of 0 or higher. So these are all early time scattering. They correspond to interactions with heavy mediators, things that have derivatives, yeah. So this is a dark matter and baryon contact interaction or higher. Okay. So in terms of, let me retranslate the plots that I showed you before into something that actually constrains the dark matter proton cross-section in centimeters squared versus the dark matter mass in GeV. And I can just take various models with different velocity dependencies and show you the lines that Planck excludes for the various models. So the thing I want just to note is that for this particular plot, I've evaluated all the cross-sections at v of 220 kilometers per second, just so I could put them all on the same plot without having an enormous log scale. So everything above this line, for instance, is excluded. Now, one of the aspects that I haven't talked about that we also have observational data for is not just the anisotropies of the CMB, but we also have what's called the matter power spectrum. So the matter power spectrum is just an indicator of how much matter there exists on a variety of scales. The scale is given as inverse megaparsecs. And this matter power spectrum from lambda CDM is what you see in black here. Okay. So these different models that I have at their CMB limits will peel off from this lambda CDM prediction and give you a suppression at higher K or smaller scales. Okay. So that's fine, but if we actually look at data, we can see that as this matter power spectrum drops off, there are data points that are constraining the matter power spectrum to not have such a drastic drop off in terms of suppression. So there is definitely data here that is constraining these models beyond what the cosmic microwave background is able to do. Okay. So we can imagine what is the smallest, let's go out to the smallest scale that we can think of and constrain these models at that scale, and that will give us one of the more stringent limits on this model. And so some of the smallest objects that we have that are dark matter galaxies are called Milky Way Satellites. These are sub-halos of our Milky Way. So our Milky Way galaxy is sitting here, and the Milky Way halo is out here. And so these sub-halos, or these satellite galaxies, are hosting their own galaxies that are bound to the Milky Way. Okay. And so we've seen a handful of these objects. I'm just showing the objects that have been identified. These are classic objects that we've seen for a while. These in blue were identified by the Sloan Digital Sky Survey. And we can say that our dark matter interaction should not suppress structure enough such that these objects don't form. Okay. And so a sort of back of the envelope way to estimate what the cross section should be is to look at when your momentum transfer rate equals your Hubble rate. There's a lot of interaction still at that point, and so it's suppressing structure a lot on that scale. So we can say, how far are these peaks separated at that time, and just say, take that mass that is supposed to fit inside that mode, and say that mode, that we know that mass is going to be destroyed. No structure is going to be able to form with that mass. Okay? So we can do this back of the envelope calculation, and then I'll explain to you a more rigorous way to do this. But to kind of set the scale for how the Milky Way satellites are able to constrain this interaction, I kind of want to show you and give you perspective of some other experiments first. So here's the cross-section in centimeters squared, and here's the dark matter mass in the x-axis. And hopefully you can see it. There are some outlines of different experiments. So first of all, direct detection. Direct detection is, first of all, way down here normally. So this is 10 to the minus 34. We are looking at things like 10 to the minus 40 to 46. So direct detection, if you increase the cross-section high and high and high enough, then there will be some ceiling that these authors have estimated, beyond which the experiment cannot say if there's a dark matter event. They just lose sensitivity. Okay. There is X-ray quantum calorimeter. This was a sounding rocket that took data for 100 seconds. And from that 100 seconds, they were able to place limits on any anomalous interaction that the rocket may have had or the calorimeter may have had with a dark matter particle. And so there are very high cross-sections that have been excluded because of this work. I will note that there is also work by people here who have constrained these large dark matter interactions with molecular clouds. I only showed these two because these constraints kind of kick in more strongly at higher dark matter masses. So I was for this particular plot that was published, we just put in sort of the outline of what's ideal for this dark matter range. There are also these cosmic ray upscattered constraints. So the idea here is that you can go to lower dark matter mass, and normally these wouldn't have enough kinetic energy to impart to have a visible nuclear recoil. But if this light dark matter particle was upscattered and had enough energy from interacting with a cosmic ray, then that dark matter particle has enough energy to then go and hit either mini boon or xenon 1 ton and make a visible signal there. And so these authors have drawn contours in this region here. I will note that they had assumed just a generic, this is all for spin-independent scattering, right? Because I want to use the most typical interaction that direct detection uses. So they assumed, velocity-independent scattering for this analysis, but they assumed that would also be the same cross-section for scattering on cosmic rays. That ends up not being okay, as was pointed out by some Fermilab people, because if you now are thinking about a relativistic process, you need to take into account the velocity dependence of a particular model. So so these are cosmic ray analysis, and just to give you an idea of where the CMB limits that I had lie, they're here. This is another paper that also used Lyman alpha data. They have constraints there. But if we have our Milky Way satellites, the sheer existence of our Milky Way satellites give us this constraint here. So the analysis that I talked about before, that's this dashed line. This is sort of the back of the envelope way of calculating the constraint. This solid line is actually taking simulations and running simulations to then look at what kind of a small scale suppression can be tolerated while not washing out structures of the size of Milky Way satellite galaxies. Okay. Are there any questions on this part of the talk before I move on to some completely different era of cosmology? Yeah.
Would the addition of more satellites then push the dotted line further down? Am I understanding that correctly?
Further down, do you mean down this way? Or?
Yeah, down this way.
So this is actually being driven by the smallest satellite we have. So we analyze the entire population of satellites that we have up to the Sloan Digital Sky Survey, and the tiniest object is the thing that's really driving this constraint. So if you find a smaller object, that is the thing that's going to bring this curve down. Now, certainly we have a lot more satellites that we have seen since the Dark Energy Survey has turned on. So I am currently a guest collaborator with DES to use DES's latest data to do that, and hopefully the idea is not only to get a smaller galaxy, but also to see if there's any dependence on what the behavior of the full population is.
And this is completely independent of arguments like if it's a 1 keV dark matter particle, then it's a warm dark matter particle, and the power spectrum is different. You suppress small scale structure. This is
Yes, that's a
completely
great
different
question.
argument.
Yes,
Yeah.
this is a completely different argument. So we cut off at about 10 keV,
Yeah.
where warm dark matter limits really need to come into play, and then you need to.
So that's why you've drawn that edge there, because
Yeah.
anything to the left of that is already ruled out
By warm dark matter.
by the usual warm dark matter.
Yeah. So certainly there's some going to be some smooth transition if you were to build
Okay.
the entire framework to include warm dark matter plus these interactions.
Okay.
But effectively you really shouldn't think of our analysis applying to anything lower than this. And the upper limit is drawn only for the fact that this limit for both the CMB and these Milky Way satellites just continue as straight lines. These are just proportional constraints. Yeah.
And this does assume that, like, once you dampen that structure on that scale, you'll never get it back. I guess you can't ever make things after the CMB structures of that scale can't form anymore.
Yeah. So we were being a bit conservative, and we were insisting that there had to be a significant amount of suppression compared to lambda CDM to say that object shouldn't form. So that's the dashed line estimate. The full population analysis takes a simulation, a cosmological simulation of something that has this power suppression. It looks very similar to warm dark matter, actually, the way that the matter power spectrum is suppressed. And my colleagues here from Stanford have developed a way to then take that Milky Way galaxy and populate it with these sub-galaxies or sub-halos. So, and they take into account effects like, the fact that you're going to have tidal disruption and things of that nature. So all of those caveats have been marginalized over in this analysis. So this is giving you some rather conservative constraint. Certainly there are improvements that we plan on making to the simulation side of things, but this is it's comforting to know that these two lines are very close to one another. Did you have a question? No. Okay.
Well, yeah. So, how do these bounds change if I consider dark matter as a subdominant component, or if I consider dark matter with large cross sections as a subdominant component?
Yeah, no, that's a great question. That's so importantly, all of these constraints have assumed that all of dark matter is interacting in this way. Certainly, if you have a subcomponent, the CMB constraints relax quite a bit, and as such, the Milky Way satellite constraints will relax as well, because the physics that is happening that is creating the CMB constraint is the same physics that is giving you this Milky Way constraint. All of this formation suppression is happening in the early universe. This is not after galaxies have formed and then you're breaking up those small halos. This is not even letting them exist in the first place. Yeah. So I know that was a very indirect answer to your question, but they both should be penalized in the same manner if you consider only a fraction of dark matter interacting. Okay. So I'm going to move on now from the story of the CMB and early universe physics and talk about something different, and this is this edges experiment. So for this, I would like to talk about interactions with light mediators, or this late time scattering. And so what I mean by light mediators is I mean any mediator that's going to have a mass that is negligible compared to the momentum transfer, so that I can write the cross-section as just some inverse power of velocity, all right? So I don't have to be concerned with what the mediator mass is. So for this case, I don't want to get into the technical details, but we do have a significantly different situation than the heavy mediator case, where you have, say for instance, for v to the -4, that's going to be the more interesting one, you have less interaction at early times and more at late. So this velocity, I've just been assuming is just the thermal velocity of particles. It's related to the temperature and the mass of the particle. And as the universe continues to expand and cool, that thermal velocity drops, right? But there's another velocity at play here, and it's the whole motion of the dark matter fluid with respect to the baryon fluid. So there's the bulk property that needs to come into play, and for the most part in the early universe at these times, that velocity just doesn't matter. The thermal velocities are so much larger. So for these models that have a lot of interaction here, we could assume that the thermal velocity was very large, and we didn't have to worry about this relative bulk velocity of the fluids. But as the universe cools, and if our interaction is relevant at later times, then suddenly we need to worry about this bulk velocity. And because of that, that leads to nonlinearities in a nice linear, otherwise linear cosmology, and that creates a lot of technical problems. All right, so I don't want to get into it. I will just explain to you, I will demonstrate this by just showing you what the equations look like. This is the temperature evolution of the dark matter and the baryons. This is the velocity, this bulk velocity evolution of these fluids for the easy case that I've already discussed. And this is what happens when you have to consider all of the bulk velocity for these, n equals -4 models. So yes, I'm not going to get into this. All I will say is that you have to treat these nonlinearities in some manner and account for them. So I wanted to break this off of the other case where you had scattering at early times, because the constraints just look very different. So here are the CMB constraints for the dark matter cross-section in centimeters squared versus the dark matter mass. And for n equals -4, v to the -4 scattering, this is what the constraint looks like. So it's very flat at lower masses, and then it starts to rise as the mass approaches GeV. And if you were to neglect everything that I said before, that I said was very important before, and just do it, the analysis, then you would get an overestimated constraint by over an order of magnitude. So the bulk velocity is very important. I'm not going to explain how you need it, but just to say that you do. So I've been focusing here on these negative powers of velocity, and what do these correspond to? What sort of models do you get out of them? So if you have a v to the -2 scattering, this is say dark matter with an electric dipole moment. So that's the velocity dependence of that particular model. A v to the -4 interaction is just Coulomb scattering. So this is dark matter that has some Coulomb-like interaction, right? So you can take two perspectives on this. You can say, I'm just going to assume I have some phenomenological model. I'm not going to worry about how it gets there or where it comes from. I'm just going to say that dark matter scatters with nucleons with this v to the -4 and not think about it anymore. Or I can say, I need to actually embed this in a realistic particle physics model. One of the easiest ones to do, since this is a Coulomb-like interaction, is just to say it's a Coulomb interaction. So if you give dark matter a little bit of electric charge, this is called millicharged dark matter, and it will scatter with ordinary particles, charged particles of the standard model with a b to the -4 interaction. Okay.
So with a Coulomb interaction, you also assume the dark matter is neutral in whatever charge has that Coulomb interaction?
So I assume that
So the bulk dark matter has no net, whatever this charge is that has this Coulomb force.
oh, sure. So oftentimes people
There's
will,
no long range force.
I mean, the
like gravity.
long range force that enters in would be the photon. The photon is providing some long range force. It's a very small force because you can't have this be strongly electrically charged.
Right.
But yes, that is something that you would have to worry about if you wanted a very high electric charge, but you're only taking a small fraction. Did that?
I think so.
Okay. So, so in the early universe, when I'm analyzing these models, I'm not concerned with what sort of interpretation I give this because the universe was completely ionized before recombination. So I'm just going to say they're ions. So whether or not it's an electric charge or some other sort of force, I can just say that scattering happens between dark matter and all the baryons with this interaction. Now, if you go after recombination and look at the dark ages, the universe is mostly neutral. So now it does make a big difference on what you assume, because if you want it to be dark matter millicharge, then you need to scatter on ions. And there are just very few ions in the universe. If you just take this phenomenological model, then you can just say, I don't care if it's, hydrogen or ionized hydrogen. I'm going to be able to scatter. And so this relates to an announcement that the EDGES collaboration made in February 2018. Before I get into that, though, I have to tell you what EDGES was. So EDGES is an experiment to detect the global epoch of reionization signature. So it's this dipole antenna that's out in the middle of the Australian desert, and what they're doing is looking for the absorption of CMB photons as they're coming from the cosmic microwave background to and absorbing in neutral hydrogen clouds. So occasionally when these photons will be absorbed, excite the 21 centimeter hyperfine transition, and then you will have fewer CMB photons that actually make it to this detector. And so this process is going to be observable right around the time of cosmic dawn. For various reasons that I won't get into, but the idea here is that they're looking for this absorption feature. It's of course redshifted away from the 21 centimeter line because the photon has then had to propagate some amount. So there's a redshift of about Z of 17 that this trough lies on, and this is what the experiment has observed. However, the issue is that in the most extreme case in lambda-CDM cosmology, you shouldn't see this large amount of absorption. So there's nominally a 3.8 sigma discrepancy between this and the observation. There have been lots of debates about whether or not what the EDGES experiment has seen is corresponds to the physics that they think. So this is this measurement should, we should wait for verification or other experiments to turn on and also look for this absorption feature. But for the moment, this is what the EDGES collaboration put out.
Can I ask briefly about this
Yes.
before you go on to
Please.
explain that? So what part of the sky does it observe?
Oh, so this is a global signal, so it's taking the full sky. So it doesn't, or the part of the sky it sees. So it doesn't care. It's not doing any angular correlation.
Right.
It's not
So
making any
taking the
map.
full sky. Does but it does like lots of foreground diffraction and things like that.
Yeah. So that's one of the major complaints about the interpretation of the signal is that if you're just we have a lot of radio signal that we create that the atmosphere causes a lot of problems for us. So the thing is that they see a signal that's on the order of, point few Kelvin, and to get this signal, they're taking something that's, thousands of Kelvin and subtracting off a background that is thousands of Kelvin to get something that is sub-Kelvin. So depending on how you have modeled your background, this could be problematic. Do you understand the full systematics of your antenna and everything like that? So the shape of this trough is also very weird. So there are some issues here, and it would be best if we had full sky or angular information from 21 centimeter, and there are experiments hoping to achieve that, and that would really kind of solidify whether or not this amount of absorption is real or not. So at the time that this this paper came out, there was an accompanying theory paper that said, hey, dark matter baryon scattering that scales as v to the -4 can cool the gas, cool these hydrogen clouds, such that essentially they can absorb more CMB photons. And then you can get a larger absorption trough. So this was a theory paper that came out, and if we compare that to what the CMB says the limit is for this process, we see that this is the cross-section that's needed to explain edges. But here I've been plotting the dark matter hydrogen cross-section. So if you actually want to put this into the context of, say, a millicharge dark matter model, this line has to be essentially punished by whatever the ionization fraction is post-recombination. So you would have to take this line and move it up orders of magnitude, and it would be excluded by the CMB. So 100% of this dark matter millicharge would not be a viable candidate for explaining this absorption feature for edges. There are other ways that you can explain the edges result, but I'm not going to get into it. Instead, I'm going to very quickly talk about this idea that you can go to smaller dark matter fractions. Let me not harp on these particular plots here, but if you have a smaller dark matter fraction, the CMB can tolerate a larger amount of interaction from that smaller part of the dark matter. And the rest of the dark matter is just going to be normal, ordinary CDM. So here's the constraint at a given mass, I think this is 1 MeV, of the cross-section versus the amount of dark matter that's interacting. So you can see here, as you lower and lower and lower, the Planck data allow for a higher and higher cross-section for that fractional amount of dark matter. But you see, as you get to low fractions, that the CMB constraints essentially turn off. And this is because Planck only has so much sensitivity. And as you get to these very low fractions, the cross-section can be very high, and you can essentially couple this small amount of dark matter to the baryons so that it just behaves as a baryon, right? So you're hiding in the uncertainty of the baryon density that Planck is able to see when you get to these very small fractions, all right? And so there was a follow-up paper that we did to look at the viable parameter space dark matter millicharge. Since I'm running low on time, let me just say that there is some parameter space. It's very small. There are plenty of other constraints that come into play, and but this is just one interpretation of how to get the edges result with dark matter scattering. Yeah.
Sorry, when you're mentioning the edges results here, are you predominantly trying to measure the depth of the trough? Because besides the depth, that shape is very upsetting.
Yes. These lines that for different fractions of dark matter that give you the edges absorption are only trying to match the depth. That's it. It does not match the signal. There is no fitting that's going on here. We're just trying to get the right depth. So yeah, this is essentially what you would need, and we are being very we're being very generous in terms of the astrophysics here. So okay, so let me conclude by just saying that you know, cosmological astrophysical observations are a really complementary way to look for dark matter interactions with the standard model. You know, we have future CMB experiments. Here are current ground-based experiments that are running SPT and ACT. If they're on the ground, they can be built bigger, so they can see smaller angular scales, but they can't see the full sky. But these get down to smaller scales, and we have future generations of experiments that are being built. In terms of 21 centimeter, we would really like the actual power spectrum. We'd like the angular information to be able to subtract those backgrounds efficiently and to know what's going on at this area, this era of cosmic dawn. And then galaxy surveys, we have DES, that we have a lot more dwarf spheroidal galaxies that we see in the satellites in the Milky Way, and the future LSST, the Large Synoptic Survey Telescope, which has recently been renamed in honor of Vera Rubin, we'll see even more. So there's a lot of interesting experiments that are upcoming that will help give us some insight into this dark matter problem. So happy to take any questions, and thank you.
Time for one or two quick questions. Sarah?
Kind of combines the first part of the talk with the second. So I think this idea of having another mechanism that knocks out some of the halo sizes is really interesting. And so I was wondering, do you have an idea about the halos that we kind of say we kick out at redshift 0? Do you know roughly what size they were around the cosmic dawn? Because if you knock out some critical halos there, we might get some other constraints from 20
That is
centimeter.
a great question. That is an answer I cannot give you because I'm working on it.
Okay.
But yes, that is exactly right. You're also going to want to be sure you form structure at earlier times as well, and you need that structure to be around in order to get what we see today. So that is another constraint that is at play, and so we're in the midst of that at the moment. Yeah.
Maybe one very quick question. So when you're talking about these very small fractions of the dark matter that you're using to cool the gas, do you need to worry about the fact that you're heating up the dark matter and all that heat might just, you know, heat you up to the point that you can't cool? You can't efficiently cool
Oh
the
yeah,
gas
the sort of the lines that we drew that are ideal or optimal for edges, you can actually see the evolution of the dark matter temperature rising and pulling down the baryon temperature, and eventually those two meet and
so that's
thermalize.
what's going on there.
Yeah.
Okay, I see. Yes. Cool. All right, let's thank him again.